Hi, my name is Fakia Selassie. I took the last 6 days off from anything to implement ideas that I have had for the last year. So basically, I had 4 ideas that I thought were really good and tried to implement them just in 6 days. So from 4 of it, 2 of them worked really well, more than I expected, and 2 of them completely flopped. Really embarrassing. So let me start from the ideas that actually worked. The first one was a visual learning tool that I was thinking, since most of my favorite YouTubers like Bertasium, 3Brown 1Blue, uh, and also others were really visual communicators. I was like, what if everyone can have this on demand, right? But that was not the only thing. I also wanted to do the tool to generate a full course, or the tool to give you any visualization that you want, rather than doing it in video editors, like trying to do every detail. What if you just explain what you want in natural language and it visualizes anything that you want, and you can just take that and use it in your video? So that was the plan, and I was thinking this can be used by students, video editors, course creators, educators, YouTubers. And I tried to implement it, and it actually kind of worked. Uh, for now, I tried it on Matt's videos, and I will show you a demo right here, and it's working really well.
To understand the Fourier transform, start with a complex signal. It looks messy, but it is actually just a combination of several pure, simple sine waves added together. The Fourier transform is the tool we use to reach into this soup and pull out the individual ingredients. Imagine taking our signal and wrapping it around a circle. We can control the speed at which we wrap it. If we wrap it at a frequency that doesn't match the signal's internal rhythm, the wave gets tangled and stays centered around the origin. But something special happens when the wrapping frequency perfectly matches the frequency of the signal. The peaks of the wave all align on one side of the circle, causing the entire shape to shift its center of mass away from the origin. By tracking how far that center of mass moves for every possible wrapping frequency, we create a new graph. This is the frequency domain. Each spike in this graph tells us exactly which pure notes were hidden inside our original messy signal. To understand a transformer, forget about sequences for a moment and think about context. In older models, words were processed one by one, like beads on a string. But a transformer looks at every word in a sentence simultaneously. It treats a sentence not as a line, but as a fully connected network, where every word can talk to every other word to figure out its specific meaning in that context. This talking happens through a process called self-attention. Each word is turned into 3 vectors: a query, a key, and a value. Think of the query as what the word is looking for, the key as what the word can offer, and the value as the actual information it holds. To find the meaning of the word bank, it sends its query to the keys of all other words. When a query matches a key, they create a high attention score. This score determines how much of the value from the other word should be mixed into the current word. If the sentence is about a river, the word bank will have a high match with water and flow, pulling their information in to update its own definition. This happens for every word at the same time across multiple heads, allowing the model to understand different relationships simultaneously, like grammar, tense, and sentiment. Finally, these updated meanings are passed through a standard neural network to refine the results. By stacking these layers, the model builds a deep, nuanced understanding of the entire text at once.
Okay, what is the next idea that I tried to do? It's called the Verifier app. It is basically a web app that will help the local businesses here in my country. So the problem is this: whenever we have a transaction, buying something and then paying it online, we just show a screenshot and the receiver just takes a picture, believing us. Most of the time they have a latency and you might not get a text right away before I go. So a lot of businesses just get scammed by fake screenshots or fake mobile application that generate kind of a fake confirmation, and people just take a picture and get scammed. So I was like, this can be actually solved using software. So I tried to build a web app. What it does is basically you take a picture of the screenshot and it extracts every information that is claimed in that receipt and take the transaction number, try to go online, find the receipt using that transaction number, and try to verify if every information that is claimed in that receipt is actually true. Is the receiver name correct? Is the time that the receipt is saying and the online receipts talking the same thing? So yeah, it tries to confirm everything, and if one of them is wrong, it just tells you suspicious, this information is not right. And you might check it, and for example, if it's a time issue and if it's just 1 millisecond or that kind of a difference, you might check it and like, oh, it's okay. But it technically verifies like whatever transaction you would have, and I try to wrap it up using a Telegram mini app, since everybody in here uses Telegram. Okay, now let's move on to the two embarrassing failed ideas. So the first one was an LLM parallelization problem. Basically, trying to parallelize LLM inference using edge devices, which is basically a fancy way of saying, what if I contribute my phone, you contribute your computer, your phone, everyone contributes, and we will have our own LLM deployed across all those devices, and we can use that AI for free whenever we want. So the concept of parallelizing LLMs by itself is not a new idea. Like, every data center does it, and there are really famous papers that talks about this. They're called like the Galvatron, Megatron, and they're basically how do we parallelize LLMs through GPUs. Yeah, but the problem I knew was a bandwidth and a latency bottleneck across the networks. So as much as you can parallelize many devices, you can have the computing power, but the computing power is not the problem. Even in GPUs, it is the bandwidth that's the problem. So how I was thinking to solve the bandwidth and latency problem was to compress the data and then transfer it from one device to the other one. And how that failed was whenever the compression algorithm was bad, obviously that took a lot of bandwidth and latency, and it didn't help at all. And whenever the compression algorithm was really good, the problem was latency, because the other device was taking so much time that the network wouldn't even take just to decompress and use that algorithm. I tried to use many algorithms as much as possible. I tried to write my own algorithm that would help with this kind of tensor compression, but unfortunately it didn't work. Okay, coming to the fourth idea. The fourth idea was basically, it was a really naive approach of, we don't need neural nets for phonetic orthography or shallow orthography languages. That is basically my main language. Amharic is a shallow orthography. To know what that means is every letter in Amharic has its own distinct sounds in whatever word you're using that letter. In opposite to English, which is basically a deep orthography, because the sound of every letter changes depending on the word and the context that you use it. So I was like, I can solve this, because you can just record the sounds once and then use amplitude or frequency smoothing whenever they are concatenated so that they don't look isolated letters, and use them. So to get that smoothing functions, I recorded another 120 words and tried to compare the concatenated letters with the actual words. And it did not work, because the smoothing function, or how the amplitude changes whenever we are saying a word, completely depends on the word and the letters that we're using on the word. So for example, if you're having a certain kind of amplitude graph when you're saying a certain word, it's completely different from when you say another word. So that was basically a pattern that a neural net have to learn, maybe. So yeah, we absolutely have to use a neural network to do reliable, natural sounding language. So maybe not generating the sound like other languages do, but we can teach the neural network the difference in the amplitude progression of whenever every word is said and which letters are forming that word, and it can learn which pattern happens depending on the word, and it can basically concatenate your pre-recorded sound to generate a good idea. But my own assumption first was we don't need neural nets to do speech generation. I mean, concatenative speech is a very common thing, but we don't really need it to make a natural sounding speech from a text for shallow orthography languages, but it actually didn't work. So right now I'm going to be working on Bestie and Verifier, and mainly on Bestie. And if you're interested in every detail that how I implemented Bestie, it is not a video generation tool or an image generation tool. I am explaining that in the next video. See you there.